So when you say cold, are you referring to like this term cold matter and hot matter?
No. Just not just to the point where there's the thermal energy no longer exceeds the gravitational energy. So when something's hot, when a cloud is hot, it's actually supported by thermal pressure. And as it
Okay.
cools down, that thermal pressure stops, and you start to get a gravitational collapse of a cloud into a star.
Okay. Oh wow. Okay.
Yeah. So yeah, you need to cool down hot stuff in order to make more hot stuff. But and then it's actually pressure that stops the star from collapsing even further, right? As the temperature and pressure increases and squeezes together the protons at the center of that star in the thermonuclear fusion process, that generates enough energy to support the star again against its own gravity.
So
So
these are no, these are good. These are definitely really good points because, I mean, how do we know, for example, the process that creates a star? Obviously, you've just explained it, but how is that? How is it we came to those kind of conclusions?
well, so it started off asking some very basic questions. Why is the sun bright, right? And so we knew that there's fire, right? So you burn wood, you get fire. Is the sun made of wood? Well, we know the mass of the sun, right? We know how much stuff the sun is made of, and we know how big it is,
So
right?
I
So
guess even
could
the
it be a
mass.
wooden?
So
Yeah,
so how do
yeah,
we know the mass? Is that some gravity
yeah.
calculation?
So once you have Kepler's laws and Newton's laws, and you know how far away the Earth is and how long it takes the Earth to go around, you can calculate the mass of the sun. And it's the same physics for calculating the masses of other stars as well, particularly in binary systems. So if you know the separation and the orbital period, you know what the masses are going to be. It's from Newton's laws of
Yeah.
gravitation that you do that.
Okay.
Yeah.
Cool.
So we know the mass and the size of the sun as soon as we knew we already knew the rotational period of the Earth is 1 year. So as soon as we knew how far away the Earth was, and we started to get a sense of that from Kepler, right? So Kepler's laws, Kepler's third law is the period squared equals the distance from the sun cubed. We started to get a sense of that relatively. So we knew that, say, Venus was 72% the distance from the sun that the Earth was. So this is where the astronomical unit comes from, right? So here's a trick that you probably remember, right? Is that if you don't know what the number is, you can redefine how you tell people what that number is and just call it 1, right? So distance is measured in meters,
Yeah.
but we don't know how many meters it is from the sun to the Earth. So we'll redefine that as a distance and call it 1
Oh yeah,
astronomical
yeah, yeah.
unit, right? And so as
Yeah.
soon as you've got a 1, everything becomes relative, right? So you know if it's less than 1, it's closer to the sun. If it's farther away, if it's more than 1, it's farther away. So the Mars is 1.5 astronomical units from the sun. So it's 50% farther away than the Earth. Now, the reason we actually now know how many meters there are in an astronomical unit is because Venus actually transits in front of the sun every 100 and something years. And so if you're at 2 different points on the Earth, you can actually use parallax to get a distance to Venus. And because you know Venus is 72% the distance to the Earth from the sun, you now then can back that out to get the distance to the Earth itself in astronomical units. So